right, welcome. If you're prepping for your FRCR physics exam, you are in exactly the right place. In the next few minutes, we're going to break down the absolute heart of all X-ray imaging, how photons actually interact with the human body. Get this down, and I promise you'll start seeing every image in a whole new light. So let's jump right in with a really fundamental question. We've all seen a million X-rays, right? But have you ever really stopped and asked why it looks the way it does? I mean, a regular camera just sees reflected light. It can't tell the difference between bone and skin. But an X-ray, well, an X-ray sees something much, much deeper. And the answer to this question is, quite literally, the foundation of our entire field. And here it is. The answer is a term you absolutely have to know: differential attenuation. It sounds fancy, but the idea is actually super simple. As an X-ray beam flies through the body, some tissues, like bone, will stop a lot of it. Other things, like air, will barely stop it at all. That difference in stopping power, or attenuation, is what creates the image. Seriously, without this, an X-ray would just be a foggy gray mess. This one principle is why radiology even exists. Okay, so how does this attenuation actually happen? Now, technically, there are about 5 ways an X-ray photon can interact with matter. But for diagnostic imaging and for your exam, you really only need to care about 2 of them. I want you to think of them as 2 characters in a story. We've got the hero, the one who creates the beautiful contrast we need, and then we've got the villain, the one who just wants to ruin the picture by covering it in fog. So let's meet our characters. On the left, we've got our hero, the photoelectric effect, our contrast king. In this interaction, the X-ray photon comes in and gets completely zapped, totally absorbed by an atom. This is fantastic for us because it's what creates those sharp, beautiful differences between tissues. But then, on the right, you've got the villain, Compton scattering, the fog generator. Here, the photon just kind of bumps into an electron, loses a bit of steam, and then ricochets off in some random direction. It doesn't help us see anything, it just creates noise that degrades our image. So what's our hero's superpower? What makes the photoelectric effect so good at creating contrast? It all comes down to one absolutely critical relationship. The chance of it happening is proportional to the atomic number of the tissue. We call that Z cubed. And no, that's not Z times 3, that's Z times Z times Z. This exponential power is the secret sauce. It means that even a small difference in atomic number between 2 tissues results in a huge difference in how many X-rays they absorb. And check this out. This is where it gets crazy. Let's put some numbers to it. Bone has an atomic number of about 13.8. Soft tissue is around 7.4. So bone Z is roughly double that of soft tissue, right? But because of that Z cubed rule, the chance of a photoelectric interaction isn't just double, it's about 8 times higher in bone. That massive difference is precisely why bones pop out so bright and white on an X-ray. And what about our villain, the fog generator? Compton scattering is the complete opposite. It's basically blind to the atomic number. It couldn't care less. Instead, it just depends on electron density, pretty much how jam-packed a tissue is with electrons. And it turns out, that's surprisingly similar across most tissues in the body. So Compton scatter just happens kind of everywhere, equally. It does absolutely nothing to help us tell things apart. It just adds that uniform gray fog that washes out all the beautiful contrast our hero works so hard to create. Okay, so we've got this epic battle raging inside the patient. Contrast versus fog. So what? Well, here's the cool part. We're not just helpless bystanders. We are actually in control. By choosing our technique, specifically the energy of our X-ray beam, which we measure in kilovolt peak, or kVp, we get to decide which one of these interactions is going to be the dominant player. And this table shows you exactly how we do that in the real world. Take a look at the top. Mammography. Here, we desperately need to see tiny, subtle differences in soft tissues. So what do? We use a really low kVp that cranks up the photoelectric effect and gives us that amazing high contrast. Now jump down to the bottom, a chest X-ray. The game is completely different. Here, we need our X-rays to punch through the dense heart and all the stuff in the mediastinum. So we use a high kVp. That favors Compton scattering, which gives us the penetration we need, even if we sacrifice a little bit of contrast. It is always a deliberate choice. But wait, that leads us to the next logical problem, right? We just said that for some exams, like a chest X-ray, we have to use high kVp techniques. That means we are knowingly creating more of our villain, Compton scatter. We're making more fog on purpose. If we just left it at that, our images would be a washed-out mess. So how do we fight back and get rid of that fog? Yeah, this is a huge challenge in radiography. You've just created this cloud of useless image-degrading scatter photons. They're flying out of the patient at all kinds of crazy angles, ready to hit the detector and ruin your picture. We need a way to somehow filter out all that junk before it gets to the detector, but at the same time, let all the useful, straight-flying photons through. How on earth do you do that?
The answer is an incredibly clever little device called an anti-scatter grid. The way it works is just brilliant. Think of it like a set of tiny Venetian blinds sitting right in front of the detector. All the useful primary photons are traveling in a straight line, so they fly right through the gaps. But all those scattered fog photons, they're coming in at weird angles, so they slam into the thin lead strips of the grid and get absorbed. It's an amazingly simple and elegant way to clean up the image.
But, and this is a huge but for your exams, there is no such thing as a free lunch in physics. That grid is amazing, but it's not perfect. It accidentally absorbs some of the good primary photons too. So to make sure we still get a good quality image, we have to crank up the initial radiation dose to the patient. And that increase is significant, usually by a factor of 3 to 5 times. This is called the Bucky factor, and it's a critical trade-off you have to understand. We accept a higher patient dose in exchange for a much clearer, higher contrast image. Okay, let's bring it all home. We're going to wrap this up with the absolute must-know high yield points for your exam. If you forget everything else from this talk, please, just burn these next few points into your brain. This is the stuff that matters. Here it is, all on one slide. Let's run through it fast. Photoelectric effect, that's your contrast, and it depends on Z cubed. Compton scattering, that's your scatter or fog, and it doesn't care about Z. So, a low kVp technique maximizes the photoelectric effect, giving you high contrast. A high kVp favors Compton, giving you better penetration. And finally, grids are your tool to clean up scatter, but the price you pay is a higher patient dose. Got it? This is the whole story. And I absolutely love this quote, because it just cuts through all the noise. For your day-to-day work, and definitely for your exam, this is the golden rule. Photoelectric is your friend, it gives you contrast. Compton is the enemy, it gives you scatter. If you can just understand the battle between these two, you'll understand why every X-ray image looks the way it does. So, I'm going to leave you with this challenge. The next time you pull up a CT scan or an X-ray, don't just see anatomy. I want you to see a map of physical interactions. Every single pixel, every shade of gray from brilliant white to pitch black is just the final result of that battle between the contrast king and the fog generator. So, can you now look at this image and explain the physics behind why the bone is white, why the air is black, and why the liver is that specific shade of gray? Because once you can do that, you're not just looking at pictures anymore, you're reading the story of physics. Thanks for tuning in.